What's up, everyone? So in this video, I'll go through the formula used to solve for the correlation coefficient. A little disclaimer, I guess, before I talk is one thing to keep in mind is that you might not necessarily need to use this formula. Other than statistics classes where you might need to do this for like a test or an assignment or something, most of the time, the way you use correlations is really just for interpretation, right? So you're really just using it to interpret how two variables are related with one another, right? Like their direction or the magnitude of their correlation. So take this video with a grain of salt, right? Like if you don't need to know anything about the formula, maybe this video won't help you, but I'm hoping that I can provide you with some new insights into what correlation is, because I'm really going to go into in depth about how to interpret this formula. So anyways, moving on, as you can see, the formula is in front of you. It's quite a big formula, and before I discuss like all the individual variables, I'm actually going to rearrange it in a very specific way, and you'll see why. So if you remember in one of the previous videos, I kind of commented on this, like it looks very funny, like it's in a separate term, 1 over n minus 1, when in reality, all it really is it's just the denominator, right? So the way you can rewrite it is like you could just get rid of this and put the whole thing over n minus 1, right? That's really all it's saying, but I guess they need to put it in a nice fancy way. So what I'm going to do is I'm actually going to rearrange it like that. So I'm going to put most of this term on the left, on the right here, and put it on the numerator, except for the two values here. So the two, if you remember, S is the standard deviations. So I'm going to leave the standard deviations for variable X and variable Y in two separate terms, but I'm going to put everything else on the numerator. And you'll see why in a second. So the way I'll write this is R is equal to sigma xi minus x bar yi over n minus 1 times, so this is the two reciprocals of the standard deviations in separate terms. The reason I did this is because the term on the left is actually the formula for something else. It is the formula for the covariance. So I'll write that down. It is the covariance formula. And the symbol for covariance, it's C, or specifically CXY is what it is. And so then the other way you might see this formula written, and I think it was in my one of my psychology statistics classes, the way it was written is correlation between, correlation between variables x and y is equal to the covariance divided by Sx times Sy. So as you can see, that's actually the same thing as what's this big one at the top. It's the whole covariance divided by the two standard deviations. And you'll kind of get a feel as to why you have to divide it by Sx and Sy as I start talking about it. So what is covariance? Covariance is actually very related to correlation, and for all intents and purposes, it's basically the exact same thing. Specifically, the way the textbook likes to explain covariance is it's basically the degree of association between the variability in two distributions of scores. Or in other words, it's a measure of how much two random variables change with one another. And if you think about that, that's actually the exact same thing as how I explained correlation, right? It's the relationship between two variables. So, or in other words, how does the change in one variable relate to the change in the other? So if you remember, an increase in one variable and an increase in the other, or same idea as a decrease in one variable with a decrease in the other. So if they're in the same direction, that means it has a positive correlation because they're changing in the same direction, right? So it's positive. Same idea for covariance. So that would be considered a positive covariance. On the flip side, if they change in opposite directions, so an increase in one variable leading to a decrease in the other, well, that's a negative correlation and also a negative covariance. So really, they're the exact same thing, but the main difference between the two is that covariance, okay, the main similarity first between the two is that they both tell you about the direction, right? So the positive and negative is the same idea, except covariance can't tell you anything about magnitude. That's because it's not a standardized measure. So, for example, if you use a certain variable that has big numbers, so like an IQ or SAT scores or something like that, that's going to lead to a bigger magnitude for covariance. Whereas correlation, on the other hand, it is a standardized measure. It doesn't, the magnitude that you interpret is very intuitive, right? So it doesn't matter if you have a big measure or a small measure. The numbers, if you remember, are only between -1 and +1. And so they're standardized. And so if one set of variables has a correlation of 0.5 and another set has 0.5, those mean the exact same thing. But if you were dealing with covariance, it might not mean the same thing, right? So that's the main difference. So if you think about it, the whole point of dividing it by the standard deviations of the two variables is just that. Because remember, this is correlation, right? Correlation, it needs to be able to be standardized somehow, and that's how it's standardized, by dividing it by the standard deviations of the two variables. So one way to say correlation is basically the covariance divided by the standard deviations, and that allows it to be standardized. And that's the same thing that's being said here, right? It's the in the big one, it's the correlation divided by the standard deviation, or multiplied by the reciprocals. And so thinking of standardization, that you basically do the exact same thing when you're dealing with z-scores, right? Is you divide it by the standard deviations, because that gets rid of the units, right? So that causes the correlation, so thinking of correlation, it causes it to be a value between -1 and +1, and you want that, right? You want it to be easy to interpret. So moving on to the bigger formula, it's really quite straightforward. Now that you've kept this in mind, right? So now that the whole point of this is to standardize it. So now ignoring that and just dealing with the covariance formula on the left, basically what it's telling you is, so it's sigma, so you take the sum of whatever's to the right of it, right? So sigma. So you take the sum of the cross product. So what is a cross product? So if you think of the two variables, so x and y, so let's say x is a distribution of the variable for IQ. So it's a bunch of scores for someone's IQ. So xi would be any random score for the IQ variable, and then you subtract the mean of that distribution. So that's a deviation score, right? And so then you take the deviation score for IQ and you multiply it by the deviation for the other variable. So let's say it's like GPA, and it means the same thing, right? So yi is any random score in the GPA variable minus the mean. And this is actually not random. When you multiply a set of scores, right? So one deviation from the IQ distribution and one deviation score from the GPA distribution, they have to be linked to one another. So they have to be, like, for example, from the same person. So, like, for example, if it's my IQ score, so this is my deviation, right? My IQ score minus the mean multiplied by my GPA minus the mean. And that's the whole point, right? Because we want to see how it's correlated. So why would you do two random sets of scores with one another, right? You want it to be from, like, the same person, or the two scores that are linked, and then that's the whole point of a cross product, right? And thinking of keeping that in mind, you might actually kind of get a sense of how correlation works, like how the directionality works. Because, so say for example my IQ score was larger than the mean, this would be a positive value, right? So let's put a plus. And let's say that also my GPA score was larger than the mean. So then that would also make this a positive value. And so then that's why, if that happened, so let's say that happened for every single score, well then that would end up making the final value positive. And so then that would be a positive correlation. But on the other hand, say it was the opposite. So say let's say that my IQ score was also larger than the mean, but my GPA was lower than the mean. well then that means that these two variables are doing the opposite thing, right? While one is increasing, the other one is decreasing. And let's say that happened for everyone, well then that would lead to a negative correlation. So then really that's the main thing that you need to understand when trying to interpret this. Because you take the cross product for every single score, right? So then you add up all of them and you take an average, right? By dividing it by n minus 1. N is just the number of scores within the distribution, right? The overall number of scores. So say you have 3 scores, 3 IQ scores, and 3 GPA scores, well then that would give you 6, right? N is 6. I believe, or it could be n is equal to 3, but I'm pretty sure it's the total number of scores, but don't quote me on that. So it could be either the number of scores within each group or the total number. I actually can't recall which one it is. But anyways, that's not necessarily important. Actually, it would be the total number of scores, I'm pretty sure, because you're taking the cross products. So because you're dealing with both groups, right? Sorry, don't quote me on that. But because you're dealing with both of the variables at once, n would represent the overall number of scores, right? And so, and minus 1 because you're probably dealing with samples from the population. And so anyways, basically by dividing it by n minus 1 is you're taking the average trend of the cross product. So you're adding up all of the cross products, and if most of them end up being positive, then you're going to have a positive correlation. And if most of them end up being negative, you're going to have a negative correlation. And if they go all over the place and they cancel out, that's going to give you a correlation of 0, which means that there's no trend between the two variables. And so, yeah, I hope that makes a little bit of sense. I hope I didn't confuse you there, but essentially that's the point of correlation. It's comparing the deviations from one variable with the deviations from the other, taking the average, and then standardizing it by dividing it by the standard deviations. So I hope that helped a little bit. Thanks for watching.